All right, so you can see the screen. All right, so this is what we were doing last time, right? So we just have to finish this last part where what we had was we had a cotton and we were measuring the length of the cotton, right? And now we'll use the same cotton, and this cotton is wounded around a wooden rod. So you see this is
your
the
voice
wooden.
is lagging.
Can you check your internet connection?
Your
Because I
voice
think
is
from
lagging.
my side it's okay. Is it still lagging? Hello? Okay, is the voice still lagging? Can you confirm? Can anybody confirm that you can hear me properly?
Yeah, I can hear you completely fine.
Okay, great, good. All right, so this is what we were doing last time. So I think, Urva, you had a question last time. And I think that was, can you please remind me of your question? We were doing this, and then I think you had a question and then the class ended at that time. Can you remind me what was the question?
I don't remember. It was probably why it was 14 point something. Where is it? I don't know.
Oh,
Why
right,
did you
right.
go
I
for
got
yeah?
it. I got it. I got it. So we had this part where the left hand end of the cotton is moved to the 1 centimeter mark. So you're taking this. Okay, so you can see the pointer. You're taking this thing, and you're moving it to this mark, 1 centimeter mark. So you're just taking the cotton and you're moving it to the left. Obviously, this part will also move to the left, right? So the cotton would slide to the left. Now, they're saying with an arrow where the right hand end will reach on the ruler, right? So if I move this thing to the left at 1 centimeters, then where would this thing be? It would be at 1 centimeter mark, right? So I have to check how much distance did I move this end. So I can just do that by subtracting from 2.4. I can subtract 1, right? Because I'm subtracting, because I'm moving to the left. So from 2.4, I'll just subtract 1, and that will give me 1.4. So which means that I have moved this end 1.4 centimeters to the left to make it reach this 1 centimeter, right? So if I've moved this thing 1.4 centimeters to the left, then obviously this part will also move 1.4 centimeters to the left, right? The entire cotton would move 1.4 to the left. So if I want to see where the right end would be, I will subtract 1.4 from this value where it is at right now, right? So it's at 15.6. The right end is 15.6. So I'll just subtract this distance 1.4, which is moved to the left. 1.4 moved to left. Now, because it's to the left, I'll subtract from 15.6. I'll subtract 1.4, and that would give me this thing, 14.2 centimeters. This means that this end will be now sitting at this point where I marked with this tick, right? So it will be over here. So the new, if I were to draw this cotton, it would be something like this. Okay, so that was a very bad drawing, but I think you get the point, right? So it would be sitting over here, and it's this end would be sitting over there, right? So it will be something like this. So does that make sense? So this is the new location of this cotton.
It makes sense.
Is that clear? Okay.
Yeah.
Okay, good. All right. So the next thing was the next part is that I take the same piece of cotton that I have measured, right? And the length of this cotton we have measured to be 13.2, right? So the cotton is 13.2 centimeters long. Now we are going to wound this cotton around a wooden rod, as you can see over here. And they're saying that this rod has a square cross section. So when I round this cotton, it will form a square-like geometry, as you can see in this figure as well, right? So the cotton goes around the rod exactly 3 times, which means that this big length, which was of 13.2 centimeters, this length of cotton wraps around this rod 3 times, and then it's completely wrapped, right? So you can see that this end meets this end. So it's, if you could draw this line like this, that means that the entire cotton has covered all of its distance that it could around this rod. So they're asking you calculate the thickness of the square wooden rod. So what we're doing is really we are using the cotton whose length we already know, and we're using that to figure out the thickness of this rod. So anyone can tell me how would we go about this problem?
You can divide it by 3. The length of the
Divide by. Okay, so all right, so you're saying that we would the length of this rod, the cotton, which is 13.2, right, will divide it by 3. So that you're saying this would be 13.2 centimeters divided by 3. What's the reason for this? Why would you think that we would be doing this? Sorry, I cannot hear you. Can you please repeat again?
because it wraps around the rod 3 times.
Right. So it means that once it wraps around the rod, we only want to find out the thickness of this, what do you call this rod, right? So how thick is this rod like this? So if the cotton is wrapping 3 times around it, I just need to figure out how much of it wrapped one time, because the one time that it wrapped, it would give me this thickness over here. So if it's wrapping 3 times, then just to get the part where it wrapped one time, the length, so I'll just divide the total length of this, what do you call this cotton, we'll divide it by 3 because it wrapped around 3 times. So once I divide this by 3, it will give me 4.4 centimeters, right? This 4.4 centimeters is that length.
3.3.
13.2 divided by 3. It would be 4.4, right? I think it should be 4.4. Yeah. Okay. So it's 4.4, and this 4.4 centimeters is implying that this I keep forgetting, what is it? Cotton, right? So this cotton wrapped one time. So you can say that maybe this part of the cotton was wrapped around this rod one time, and that's 4.4 centimeters. Now, if it wraps around one time, so you can think about this, it's like this, right? So if it wraps around one time, then if you divide this thing by 3, the entire length of this, so that's giving you 4.4, which means that this thickness of this rod is 4.4 centimeters. Is that clear for everyone?
Yes.
Yes.
Okay, good, perfect. All right, so I think that was the last question. At this point, whoever is in the class, Taha, Muiz, and Urva, all of you attempted the homework by yourself as well? I think Taha and Muiz, you both did, right? And I think you both sent me the homework as well. I did went through it as well. How about you, Urva? Did you attempted the homework before?
Yeah, I did most
Yes.
of the questions.
Okay, all right. So I think Taha and Muiz, you got everything right as far as I know. You sent me, I just went through it quickly, and I think most of the things you got them, I think all of it was correct, more or less. So I think Taha and Muiz, everything is clear. If it's not, let me know. How about Urva? Everything is clear? When you went through it, you might have had some questions where you're saying, because you're saying that you did most of it, right? So everything else is now clear?
Yeah, it's now clear. I couldn't attempt the questions previously, but now it's clear.
Now it's clear. Okay, perfect.
Mhm.
All right. So now we'll close this thing. I'll share this one as well with you, and um, let's go back to our topic of kinematics, right? So where is O levels over here? Okay, here it is. Yeah, here we go. All right, so what was the thing that we were doing last time? I think it's, yeah, displacement time graphs, right? So let's continue with that. Before we proceed any further, let me just remind you that we were doing graphs, right? We started the topic of kinematics. We dealt with velocity, displacement, acceleration. We discussed those in quite details, right? We did we did an example as well. I think we did two examples, right? And then we moved on to the topic of graphs. And we were just starting displacement time graphs. So is there any question from any of the topics that we have covered so far?
No.
All right, no question. Okay, how about you, Urva? Any question?
No.
Okay, good. All right. So we'll then start with the we'll just quickly revise. So graphs they give you a visual representation or a visual picture of imagining what is going to happen or what is happening in a physical situation. So that's why I said that these things are really friendly for us. They make our lives easier. They do this by relating two variables. Normally you would see that you would be relating in the topics of mechanics, you would be relating a quantity, any physical quantity, right? It could be velocity, displacement, speed, and so on. You'll be relating those with time. So you want to see that how does the displacement, acceleration, or velocity changes as time moves forward. So that's what we do using graphs. The first thing that we'll be discussing in graphs is the displacement time graphs. So we'll see how displacement and time are related to each other. So one other thing is that these graphs can have different shapes, and all these different shapes imply a different thing about the physical situation which is happening. And we'll understand that just in a bit from now. So displacement time graphs are giving you a relation between displacement and time, obviously. So it will tell you how does the displacement vector changes as time progresses forward. Now, this was an example. So here we have two axes, right? In mathematics, you can define any graph by two axes. Let me just draw that over here. So the two axes are drawn in such a way that if one axis is drawn in a particular direction, then the other axis is always perpendicular to that axis. In mathematics, you will be seeing these axes labeled as horizontal is labeled as X, while the vertical is labeled as Y. This is completely arbitrary. It doesn't matter. You can name them anything, whatever you want. This is just a natural convention, and so some people do it this way. The main thing is that the reason that these two axes are sitting perpendicular to each other, right, at right angles from each other, makes sure that no component, no part of y is along x-axis and no part of x-axis is along y-axis. So they're completely two independent directions, right? So you can either go up or down. That's one. The other, the perpendicular to that is you can go right or left. So right or left is completely different from up and down, but you can use these two, y and x, to form another direction, which is the components of both of these directions. So for example, if I start going in this direction, then this direction would have both the components, right? So it's part of it, you're going in the upwards direction, and part of you are going in the right direction. This is the same example that I gave you when we were doing the first chapter of having a book on your table and then sliding, applying some force on the book in upwards direction and in the rightwards direction. You would see that the book starts moving in the slant direction. All right. So, okay. So I think that's too much discussion on this thing. But yeah, so that's how you define your axes. So in the same way, now when we're describing displacement time graphs, usually we always take the time axis on the horizontal axis, because that now why do we do that? So that we can take the quantity that we want to see, how does that change on the vertical axis, and then it tells you how does my y will change as x moves forward. So you take different points on x and you put it in an equation for y, which is in terms of x. As you can see right here, I'll tell you, if we come back to this displacement time graphs, you can see that this is displacement measured in meters, time measured in seconds. And you can see that this is a particular example of a graph where the slope is like this. So it's constant everywhere, right? So you can see that this slope is a straight line, and slope it means in a literal sense. You can think about this thing as a slope. I'm sure you are all aware of a slope, right? So if there's something that is at some angle to the ground, so that's called a slope, right? So if this is the ground and there is something, the road is maybe, hill upwards, then you call it's a slope at some angle theta. So this thing, if I look at this slope, if it is at some positive angle theta, then it's slope upwards, right? Now, we can compute the value of the slope by seeing how does my y changes divided by how does my x changes. So it's the ratio of change in y divided to the change in x. It's also called gradient. In this case, on y-axis, we have displacement. So I replaced y with s. X-axis, we have time. So I replaced x-axis with t. Now, this thing just means a later quantity, maybe s2 minus s1, right? So that's change in s, right? The difference between these two values divided by the corresponding change in time. So you'll have for S2, you'll have some T2, and minus for S1, you'll have some T1. Now, once you compute this thing, you'll just check on the graph. You'll start going from this T1, you'll go up, and wherever it meets this line, let me change the color of this line. Let's make it green, right? So wherever this T1 meets this green line, you'll start going in this direction to just see what would be the value of displacement at that point. And you will note that down. Now, once you do that from the graph, you'll have a coordinate. Now, this thing is called a coordinate. This is a coordinate, and this coordinate is given by T1, S1. So of course, there will be some value for t in seconds and some value for s in meters. So there will be a number. These two will be two numbers. Similarly, you can do the same thing for this thing, this coordinate. You'll go up from T2 and you will meet this line, green line, and then you will start going in this direction to see what is the value for displacement. And that would give you another coordinate, T2, S2, right? So these are known as coordinates. All right. So now having these coordinates with me, I can just substitute these values in this expression, which would give me delta S by delta T as Okay, so at this point, these coordinates are any arbitrary, but normally having a graph, you'll have some numbers there, right? So maybe this T1 could be 2 seconds, T2 could be 4 seconds. Similarly, S1 could be 5 meters, S2 could be 10 meters, right? So you'd be just putting the values S2 minus S1 divided by T2 minus T1. And this would give you a number, right? This would give you a number. Of course, with some units as well. There will be some units. So the units will be of this thing, the units will be meters from S divided by seconds from time. Now that if you know your units well, then you can immediately tell me that this thing is actually a velocity. And of course it is, because remember that velocity was defined as change in displacement divided by change in time, which means that once I compute the slope or the gradient of my displacement time graph, it will give me the velocity of the object for whom I drew this displacement time graph. So how fast is the displacement changing as time passes on? That's the slope of a displacement time graph. Now, in this case, the slope is a constant value, right? You can see that at every point, this slope is still this straight line. For example, let me give you an example. If I have something like this, for this thing, you can see that if this is the reference axis, the horizontal axis, at this point there is some other angle, at this point it makes some other angle, and you can see, so there are different angles, so which means that there are different values of slope at every point, which leads us to the fact that for whenever you have a curve like thing, curve like line, then the slope on that curve is not going to be a constant value. But before we move on to that, uh, let me ask you, is this thing clear for you? Does this displacement time graph, does it make sense? Do you understand what
Yes,
is the displacement time graph? How can I find the slope
yes,
of it?
clear.
And okay, good. And also, how is slope known as the velocity for a displacement time graph? So all of this, is this
Yes,
clear for
very
everyone?
clear.
Okay, okay.
Yes.
Urva, is it clear for you as well?
Yeah.
Okay, good, good. Okay, so then we can move forward a bit. So the main thing over here was to make you understand what is slope and how do you find out a slope of any graph, right? So you should remember this expression for any graph. So change in whatever is on the y-axis, right, divided by change in whatever is on the horizontal axis, right? Okay, so now let's talk about let's talk about this graph, right? This graph implies that if I compute the slope at some other I could have taken any 2 points, right? So maybe I could have taken this one and this one. Now usually it's a tip over here for you, that always take points that are further apart, right? I'll tell you why. Take points that are further apart. Now, why do you do that? What does that mean? That means that you want to cover as much of this line as possible. So if I take 2 points which are further apart, that is going to help me to reduce the errors, random errors, really, in my result for velocity, right? Because the further the points are, I'm sorry, can you, yes, are you saying something?
You are taking too much time.
I cannot hear you. Are you saying something? Hello.
Sir, I think you are taking too much time.
So this is clear for you? Okay. Okay, so I think I'll then, I'll start moving a bit faster. Of course, I have to make sure that everyone is understanding things, right? Okay, so the next thing is that if I have a slope, which is, well, if the slope is 0, how can the slope be 0? So we know that slope is defined as delta y by delta x. For the case of a displacement time graph, it could be 0 if change in y is 0, right? So for example, if you have a graph that looks like this, so you can see at this point there is some value of s, right? Let's just call it s1. So let's see at this time, if I go up, I want to see at this time, let's say this is t1, and let's say that at some another t2 you go up from this thing to this point. You see that at both of these t1 and t2 the displacement is same. There is no change in the displacement vector, which means that this would be s1 minus s1 divided by t2 minus t1, because both of these points, the coordinates are t2 s1, t1 s1, and that's why this thing will be 0, which means that the slope is 0. And if the slope is 0, this implies that the object is stationary or at rest, which means that it's not moving, right? It's not moving. So this is the graph that shows that an object which is stationary. Then we can move to a bit more interesting situation, right? Let's look at this thing where you have a displacement time graph, but the graph is not a straight line anymore. The graph is curved. So for example, it looks like this. Now this is a curve, right? How do I find the slope
Yes, it
on a
is.
curve? Sorry?
So the speed is x. So
Yeah.
the object is moving faster as time goes on.
Right, exactly. So the slope in this case is calculated by taking a point on this curve, right? And you draw a tangent to that point, which means that this line should be only touching this point, right? So it might look something like this, right? And for the slope at this point is then calculated by this point, and then any point on this tangent that I drew. So maybe I can take this thing, right? Now just take these 2 points and find again change in s divided by change in time. But note that for this point, this will give you the slope at this point, this one. If I want the slope at some different point, suppose I want it at this point, then again I'll draw a tangent to this point, which is a line that touches this point, and clearly I can see that the slope has increased, right? Because it is moving a bit upwards. If I draw this reference line as a dotted line like this for this thing, and then for this, clearly I can see that this angle is smaller compared to this angle, right? Suppose this is some theta prime and this is theta, then I can see that theta prime is greater than theta, which means that let's call this slope 2 and call this slope 1. Then clearly slope 2 is greater than slope 1. If the slope has increased, I know that slope was velocity. We have already established that, which means that velocity at this point at 2 is greater than the velocity at this point, which is for slope 1, which means that this graph is showing you that the velocity is increasing as the time moves forward, right? So is that clear for everyone?
Yes.
Okay, how about you, Urva? Is it clear?
Yeah.
Okay. Now, similarly, we can also have an exact same thing, but the curve is like this. So you can see that the curve is kind of starting to decrease, really. Because if I draw slope at this point, I can see it's like this, and at this point the slope becomes like this, and then maybe at this point the slope is actually 0 and then starts decreasing, right? So if I go back, if it's like this, then the slope is decreasing. Now, which means that again, you can say that the slope, let's call this slope 1, slope 2. Slope 1 is greater than slope 2. So in this case, it's the opposite, which means that slope was velocity. Velocity at point 1 is greater than velocity at point 2, which implies that we have a case of decreasing velocities. All right. So is that clear for everyone?
Yes.
Yes.
Okay, there is one interesting case I'll also like to show you guys. It's when you have a graph between displacement and time, and this graph is parallel to the vertical axis. So it's like this. What does this mean? This means that at a particular given time, time is not changing. So let's say, suppose that this is some t naught, right? At t naught, the displacement is changing indefinitely. It's increasing, but and time is not passing on. So in this case, the slope is infinity, which is also known as undefined, which means that if the slope is undefined, that means the velocity is undefined or infinity. It's not equal to infinity. You never say that. You say that velocity is going to infinity. Infinity just means very large. And in this case, the slope is very large, which means that you have to be moving with a very large speed, so that in a very at not moving forward in time at all, you can just cover so much displacement. But obviously physically that's not possible, right? Because we have a limitation on our speed, and I'm sure you're all aware of that, that your speeds can never be greater than speed of light, right? So it can never be greater than the speed of light, and speed of light is a finite value. It's not infinite. It's 3.0 into 10 raised to power 8 something, right? Depending on the units. So it's a finite value. It's not infinite. So this thing is physically not impossible, right? Okay, so that's displacement time graphs. Now we can move on. The next topic is velocity time graphs, but again, the time is almost over. If you're understanding these things easily, then let me know. I'll start going a bit faster from the next classes, right? So I think the meeting is going to end at any point. So is there any question so far from anyone?
No.
Okay, so let me, just a reminder again, tomorrow you will be having a quiz from acceleration, velocity, and displacement, right? You should understand these quantities very well. You'll be given mathematical problems, right? And some definitions as well.